Hello and good day. Gentlemen. My name is Shahid Khan and I am a chemical engineer. I have prepared a training course on process control diagrams. This course will refresh your knowledge on process control diagrams. This course is beneficial for all personnel from operators to engineers who are working in process plants, especially in oil and gas. After completing this course, you will be able to review process diagram symbols, describe a block flow diagram, describe the use of process diagrams and the information they contain, draw a process flow diagram, draw and label the following control loops: level, pressure, temperature, flow, composition, and cascade. Describe manual, automatic, and cascade control features. Identify the major components and purpose of A.N. equipment location drawing, electrical drawing, elevation drawing, and foundation drawing. Draw a process and instrument drawing. Describe the various process equipment relationships. Describe the equipment, instruments, control loops, piping, and operational data found in process control diagrams. Before starting the course, let's have a look on key terms of process control diagrams. Block flow diagram, BFD, is a set of blocks that move from left to right to show the primary flow path of a process. Controller is an instrument used to compare a process variable with a set point and initiate a change to return the process to a set point if a variance exists. Electrical drawings are symbols and diagrams that depict an electrical process. Elevation drawings are graphical representation that shows the location of process equipment in relation to existing structures and ground level. Equipment location drawings show the exact floor plan for location of equipment in relation to the plant's physical boundaries. Foundation drawings are concrete, wire mesh, and steel specifications that identify width, depth, and thickness of footings, support beams, and foundation. Legends is a document used to define symbols, abbreviations, prefixes, and specialized equipment. Piping are used to convey all kinds of fluids, liquid, or gas. Process flow diagram, PFD, or flow diagram is a simplified sketch that uses symbols to identify instruments and vessels and to describe the primary flow path through a unit. Process and instrument drawing, P&ID, is a complex drawing that uses equipment and line symbols, instruments, control loops, and electrical drawings to identify primary and secondary flow paths through the plant. P&IDs may provide operating specifications, temperatures, pressures, flows, levels, analytical variables, and mass relationship data. These documents may also include pipe sizes, equipment specifications, motor sizes, and so forth. Also called a piping and instrumentation drawing. Introduction to process drawings. Process technicians or operators, research technicians, pharmaceutical technicians, laboratory technicians, environmental technicians, engineering technicians, food processing technicians, paper and pulp technicians, power generation technicians, and engineers use process drawings or schematics to describe the primary flow and equipment used in their facilities. The I&E and maintenance departments and the construction division also use these drawings and refer to them each time work is performed in a specific section. Process schematics can vary from very simple to complex. These drawings simplify complex processes and provide a window through which a technician can study piping, instrumentation, equipment, and locations. Process schematics include symbols, block flow diagrams, process flow diagrams, control loops, operational data, and piping and instrumentation drawings. These drawings are used by every level of the plant and are a critical document. Block flow diagrams. Simple block flow diagrams can be used to show technical and non-technical people how material moves from one location to another. This picture illustrates the basic components of a block flow diagram, BFD. Block flow diagrams provide a simplistic set of sequences that move from left to right and show the primary flow path of a process. In reality, these drawings are helpful to individuals who are not expected to operate the unit. The best set of teaching tools for a new trainee is a good supervisor, a trainer, a process flow diagram, and training materials that accurately reflect the plant's standard operating procedures, SOPs. Technicians learn best when the expectations and qualification list are clearly spelled out. Most process units are very complex and provide challenging opportunities for apprentice technicians. Types of process diagrams. Process diagrams can be broken down into three major categories: process flow diagrams, PFDs, process flow and instrumentation drawings, PIDs, and process and instrument drawings, P&IDs, officially called piping and instrumentation drawings by the Instrument Society of America, ISA. A process flow diagram is a simple illustration that uses process symbols to describe the primary flow path through a unit. A process flow diagram provides a quick snapshot of the operating system. Flow diagrams include all major equipment and flows. A technician can use this document to trace the primary flow of chemicals through the unit. Secondary or minor flows are not included. Complex controlled loops and instrumentation are not included. The flow diagram is used for visitor information and new employee training. A PFID is a step up from the simplistic PFD to a little more complex drawing that includes some major and minor instrumentation and is very helpful during the training phase. Apprentice technicians will use a version of this document to trace lines, locate equipment, and check operating variables. A process and instrument drawing is much more complex. The P&ID includes a graphic representation of the equipment, piping, and instrumentation. Modern process control can be clearly inserted into the drawing to provide a process technician with a complete picture of electronic and instrument systems. Process operators can look at their process and see how the engineering department has automated the unit. Pressure, temperature, flow, analytical, speed, and level control loops are all included on the unit. P&ID cascaded control systems, indicators, and alarms are clearly visible. PFDs, PIDs, and P&IDs are used to outline or explain the complex flows, equipment, instrumentation, and equipment layouts that exist in a process unit. New technicians are required to study a simple flow diagram of their assigned operating system. Process flow diagrams typically include the major equipment and the piping path the process takes through the unit. As operators learn more about symbols and diagrams, they graduate to the much more complex process instrumentation drawings. Some symbols are common between plants, while others vary depending upon the company. In other words, there may be two different symbols used to identify a centrifugal pump or a valve. Some standardization of process symbols and diagrams is taking place. The symbols used in this video reflect a wide variety of petrochemical, gas processing, and refinery operations. Most PFDs contain design process data including flow rates, pressures, temperatures, levels, rotational speeds, equipment duties, analytical specifications, catalyst data, and so forth. Like a well-illustrated roadmap, a process flow diagram can show intricate details of an operating unit that cannot easily be noticed during a walkthrough. Process technicians are expected to memorize the company's symbols and diagram file, interpret simple flow diagrams, and apply this knowledge within hours of starting their initial training. Technicians will graduate to complex P&IDs over the course of their training and into their work careers. This picture shows the basic relationships and flow paths found in a process unit. It is easier to understand a simple flow diagram if it is broken down into sections: feed, preheating, the process, and the final products. This simple left-to-right approach allows a technician to first identify where the process starts and where it will eventually end. The feed section includes the feed tanks, mixers, piping, and valves. In the second step, the process flow is gradually heated up for processing. This section includes heat exchangers and furnaces. In the third section, the process is included. Typical examples found in the process section could include distillation or reaction. The process area is a complex collection of equipment that works together in a system. The process is designed to produce products that will be sent to the final section. Process flow diagrams. A process flow diagram is a simple illustration that uses process symbols to describe the primary flow path through a unit. A process flow diagram provides a quick snapshot of the operating unit. Flow diagrams include all primary equipment and flows. A process technician, engineer, I&E, or safety or quality manager can use this document to trace the primary flow of chemicals through the unit. Secondary or minor flows are not included. Complex control loops and instrumentation are not included. The flow diagram is used for customer information, visitor information, and new employee training. A typical plant will be composed of hundreds of smaller processes or systems. Process flow diagrams are used to illustrate these systems. New employees typically learn a series of simple flow processes as they move into more complex equipment arrangements. Given adequate time and correct instruction, it is possible to learn the most complicated process. While the concepts of lifelong learning are clearly found in the chemical processing industry, it is possible to qualify on a typical job post in 3 to 4 months. Many apprentice technicians will continue to learn and improve as they move from one assignment to the next. Basic instrument symbols. Circles or bubbles are used to indicate an instrument. The information inside the circle identifies the instrument, what it does, and the variable being measured. A line drawn horizontally through the circle indicates that it is remotely located. This typically indicates that the device is located in a control room. A dashed line indicates that the instrument is located in a control room behind the control panel. This picture illustrates what the information in a bubble means. Occasionally, numbers are located in the circle that may indicate the number of the control loop. This could indicate which system the device is in or any variety of special applications used by the company. There are a large variety of instruments and instrument symbols used in the chemical processing industry. The variables that instruments measure are pressure, temperature, level, flow, and analytical variables. If the information in a circle starts with the letter L, it is typically some type of level instrument. If the first letter in the circle is the letter A, it is an analytical instrument. This picture shows a list of simple instruments. These instruments will be covered in more detail later in this video. Process technicians use P&IDs to identify all of the equipment, instruments, and piping found in their units. New technicians use these drawings during their initial training period. Knowing and recognizing these symbols is important for a new technician. The chemical processing industry has assigned a symbol for each type of valve, pump, compressor, steam turbine, heat exchanger, cooling tower, basic instrumentation, reactor, distillation column, furnace, and boilers shown in this picture. There are symbols to represent major and minor process lines and pneumatic, hydraulic, or electric lines, and there is a wide variety of electrical symbols. Each plant will have a standardized file for their piping symbols. Process technicians should carefully review the piping symbols for major and minor flows, electric, pneumatic, capillary, and hydraulic in future equipment. The major flow path through a unit illustrates the critical areas a new technician should concentrate on. A variety of other symbols are included on the piping. These include valves, strainers, flexible spool, filters, flanges, removable spool pieces, blinds, insulation, piping size, expansion joint, vent cover, inline mixer, eductor, pulsation dampener, exhaust head, pressure rating, material codes, and steam traps. This picture illustrates the basic line symbols used by process technicians. It should be noted that not every symbol will be covered here. Valve symbols. In a refinery or chemical plant, there are thousands of different valves. These valves come in a variety of designs and sizes. Modern process control is linked to the operation of a device called an automated valve. An automated valve has an actuator mounted on the valve that is designed to open, close, or throttle flow through the pipe. A process system is a network of piping and valves. Valves are designed to control the flow of liquids and gases through the system. There is a corresponding symbol for each valve you will study. The most common valves are as follows: gate valves, ball valves, plug valves, diaphragm valves, needle valves, safety valves, pneumatically operated valves, electrically operated valves, pinch valves, globe valves, butterfly valves, check valves, angle valves, knife valves, relief valves, hydraulically operated valves, solenoid valves, motor operated. This picture has a list of valve symbols that are frequently used by technicians. Each valve has a unique purpose and design. Understanding how these devices operate is important. Being able to recognize the symbol allows a technician to understand how it is being used in the unit he or she is assigned to operate. Using a valve incorrectly can result in damage to the valve or injury to those assigned to operate the unit. Some valves are designed for on-off service, some are designed for throttling, and some are referred to as quick opening or quarter turn. While the basic function of valves is similar, it is still important to know how to safely and correctly operate each of the different designs found in your unit. Flow symbols. The basic flow elements used most commonly include orifice plates, turbine meters, rotometers, venturi tubes, mass flow meters, mag meters, pitot tubes, flow nozzles, Anyabar tubes, nutating disc meters, weirs and flumes, ultrasonic flow meters, vortex flow meters, Coriolis meters, and oval gear meters. The letters that represent these elements are FE written inside the bubble. The term FI for flow indicator is also used. A flow indicator may appear to be a simple gauge that provides relatively accurate measurements. For example, some flow indicators measure flow in GPM or gallons per minute. This picture shows the instrument symbol for flow indicator and flow element and shows how each is used in an instrument system. A common mistake is to use the symbol phi as the primary element in a flow control loop. Fluid flow can be classified as turbulent or as laminar or streamlined. Centrifugal pumps require laminar flow on the suction side of the system. Turbulent flow is useful in places on the discharge side of the pump. Fluid velocity inside a pipe changes depending upon the diameter of the pipe. These changes also have a direct relationship with pressure. In pipes where the diameter suddenly gets smaller, pressure will increase at the inlet point. Fluid velocity will increase through the narrow passage, resulting in a pressure drop. Bends in the piping will cause the liquid to become turbulent. Turbulent flow tends to transfer heat energy better. Another set of factors that will affect the velocity of a fluid is density, viscosity, and temperature increases or decreases. Many flow elements work directly with transmitters. These flow transmitters are designed to send a signal to a controller. An example of this is a differential pressure transmitter that is working with an orifice plate. The transmitter is typically mounted below the line to keep the legs liquid full. High pressure and low pressure sides are located on each side of a pressure capsule. The orifice plate creates an artificial low pressure situation inside the pipe that can be measured and transmitted to a controller. Fluid flow is typically controlled with a flow control loop, FIC. In this system, each of the 5 elements of the control loop will be flow related and labeled appropriately. It is also possible to have other flow symbols like flow recorders, FRs, high flow alarms, HFAs, and low flow alarms, LFAs. Pressure symbols. The most common pressure devices are pressure gauges, manometers, and pressure transmitters. Pressure gauges are represented on a P&ID as PI, or pressure indicator. A circle with PE is the symbol for a pressure element. A diaphragm in a DP cell is an example of a PE. A simple equation can be used to determine pressure, P, pressure equals F, force, divided by A, area. A pressure gauge has a variety of internal designs. Some of these designs use a Borden tube, diaphragm capsule, bellows, diaphragm, spiral, or helical. The basic physics has the device responding to pressure changes. These responses or movements are transferred by a mechanical linkage to an indicator. For example, a Borden tube is a hollow tube shaped like a hook. As pressure is admitted into the hollow curved tube, it attempts to straighten out. A mechanical linkage transfers this travel to an indicator that shows the pressure in pounds per square inch, PSI, pounds per square inch absolute, PSIA, pounds per square inch vacuum, PSIV, or pounds per square inch differential, PSID. This picture shows the basic instrument symbols used to show pressure. Pressure is typically controlled with a pressure control loop, PIC. In this system, each of the 5 elements of the control loop will be pressure-related and labeled appropriately. It is also possible to have other pressure symbols like pressure recorders, PR, high pressure alarms, HPA, and low pressure alarms, LPA. Level symbols. Level measurement is directly linked to pressure measurement. Controlling the level in a tank, vessel, reactor, or distillation column is an important concept. The common instruments used to measure level are level gauges, LGs, displacer bulbs coupled to a level transmitter, capacitance probes, a bubbler system, load cells, and differential pressure transmitters, delta P cells. As the level in a tank increases, the pressure at the bottom of the tank increases. A simple equation, H, height of liquid above point being calculated, times 0.433 times specific gravity equals pounds per square inch. If the liquid is in an enclosed tank, things like vapor pressure or added gas pressure must be added to the total pressure. This picture illustrates the basic symbols used to illustrate level. Level indicators are very common on process drawings and are represented with an instrument symbol that looks like a circle with LI written on the inside. The symbol LE is used to describe a level element. An example of an LE is a displacer bulb. Level is typically controlled with a level control loop, LIC. In this system, each of the 5 elements of the control loop will be level related and labeled appropriately. It is also possible to have other level symbols like level recorders, LR, high level alarms, HLA, and low level alarms, LLA. Temperature symbols. Temperature symbols are typically represented as TI for temperature indicator or TE for temperature element. A temperature indicator is typically a gauge or a thermometer. A temperature gauge has a bimetallic strip inside that differentially expands with increasing temperature, creating a deflection that is correlated with temperature. These instruments are located in the field next to the equipment. Temperature elements are typically thermoelectric temperature measuring devices, thermocouples, thermal bulbs, resistance bulbs, or resistive temperature detectors, RTDs. Temperature is defined as the degree of hotness or coldness of an object or environment. The 4 most common temperature scales used are Fahrenheit, Rankine, Celsius, and Kelvin. Each of these temperature scales has its own system for measuring temperature. Industrial temperature indicators and temperature elements can be operated in any of these systems. This picture provides a graphical illustration of the symbols used for temperature. Temperature is typically controlled with a temperature control loop, TIC. In this system, each of the 5 elements of the control loop will be temperature related and labeled appropriately. It is also possible to have other temperature symbols like temperature recorders, TR, high temperature alarms, HTA, and low temperature alarms, LTA. Analytical symbols. Analytical symbols are used to identify the use of quantitative or qualitative analyzers. Some analyzers check for the presence of a specific substance, while others check for the composition or percentage of the chemical in a process stream. Analyzers are used in the following systems. pH is used for acid-base concentration in cooling tower basin. ORP oxidation reduction potential is used for free electron concentration. Conductivity part per million is used for cooling tower blowdown. O2 analyzer is used for flue gases of boiler, furnace, or incinerator. CO analyzer is used for flue gases of boiler, furnace, or incinerator. Color analyzers are used for ensure color specifications on products. Chromatography is used for measures concentration of components. Opacity analyzers are used for identify concentration of particulates in a matter stream. Butane analyzer is used for measures concentration of butane. Some analyzers are used for measuring concentration or test for presence of a specific chemical. Some analyzers include mass spectrometers and total carbon analyzers. Analyzers provide an open window on the molecular level to the chemical composition of a substance. Like other control loops, an analytical control loop can be designed to automate a manual process. For example, the blowdown on a cooling water basin can use a conductivity meter as the primary element, a transmitter, a controller, a transducer, and a control valve located on the blowdown line. When the parts per million exceeds operational specifications, the control valve opens and allows a specific volume of water to go to the holding lagoons. This lost water is replaced by fresh water from the makeup system. The symbol for an analyzer used in this way is AE, or analyzer element. This picture illustrates the basic symbols used to describe analyzers. Since a variety of analytical variables are controlled with an analytical control loop, AIC, each of the 5 elements of the control loop will be analysis related and labeled appropriately. It is also possible to have other analytical symbols like analytical recorders, AR, high analyzer alarms, HIA, and low analyzer alarms, LAA. Equipment symbols. Pumps and tanks come in a variety of designs and shapes. Process symbols are designed to graphically display the process unit. Common pump and tank symbols can be found in this picture. Tanks may be designed as bin, drum, dome roof, open top, internal floating roof, double wall, cone roof, external floating roof, and a variety of spherical shaped tanks. The materials used in these tanks can be plastic, carbon steel, stainless steel, specialty alloys, or any variety of materials. Tanks have special designs that are shown on a P&ID and on some symbol charts. Each tank is different and has a variety of pressure and temperature requirements. Pumps come in 2 basic designs, dynamic and positive displacement. Dynamic pumps include the very popular centrifugal pump and axial pumps. Positive displacement pumps have 2 categories, rotary and reciprocating. Reciprocating pumps typically include piston, plunger, and diaphragm. These operate with a back-and-forth motion, displacing a predetermined amount of liquid. Rotary pumps use a rotary motion that displaces a specific amount of fluid on each rotation. Rotary pumps include the following designs: lobe, gear, vane, and screw. A pump and tank system includes piping, valves, instruments, and control loops as well as the pump and tank. These systems are designed to be circulated. Compressors and pumps share a common set of operating principles. The dynamic and positive displacement families share common categories. The symbols for compressors may closely resemble a pump. In most cases, the symbol is slightly larger in the compressor symbol file. In the multi-stage, centrifugal compressor, the symbol clearly describes how the gas is compressed prior to release. This is in sharp contrast to the steam turbine symbol, which illustrates the opposite effect as the steam expands while passing over the rotor. Modern P&IDs show the motor symbol connected to the driven equipment. This equipment may be a pump, compressor, mixer, or generator. This picture illustrates the standardized symbols for compressors, steam turbines, and motors. Heat exchangers and cooling towers are 2 types of industrial equipment that share a unique relationship. A heat exchanger is a device used to transfer heat energy between 2 process flows. The cooling tower performs a similar function, however, cooling towers and heat exchangers use different scientific principles to operate. Heat exchangers transfer heat energy through conductive and convective heat transfer, while cooling towers transfer heat energy to the outside air through the principle of evaporation. These pictures illustrate the standard symbols used for heat exchangers and cooling towers. The symbol for a heat exchanger clearly illustrates the flows through the device. It is important for a process technician to be able to recognize the shell inlet and outlet and the tube inlet and outlet flow paths. A heat exchanger with an arrow drawn through the body illustrates whether the tube side flow is used to heat or cool the shell side fluid. The downward direction indicates heating, while the upward direction illustrates cooling. Heat exchangers come in a variety of designs from simple to complex. Standard symbols have been developed for shell and tube heat exchangers, air-cooled heat exchangers, spiral heat exchangers, and plate and frame heat exchangers. The symbol for a cooling tower is designed to resemble the actual device in the process unit. Cooled product flows out of the bottom of the tower and to the processing units, while hot water returns to a point located above the fill. Cooling towers can be found in the following designs: forced draft, natural draft, induced draft, and atmospheric. Each of these designs has similarities and differences with the others. The symbol will not show all of the various components of the cooling tower system, however, it will provide a technician with a good foundation in cooling tower operation with enough information to clearly see the process. On a typical P&ID, distillation columns, reactors, boilers, and furnaces will be drawn as they visually appear in the plant. The standard symbols file for these devices can be found in this picture. If a proprietary process includes several types of equipment not typically found on a standard symbol file, the designer will draw the device as it visually appears in the unit. This picture illustrates standard symbols used for boilers and furnaces. The basic components and operation of boilers and furnaces are covered in boiler and furnace trainings. A furnace is designed to heat up large volumes of feedstock for chemical processing in a reactor or distillation column. Feed enters a furnace in the cooler convection section. Heat transfer is primarily through radiant and convective processes. The hottest spot in the furnace is the firebox. Tubes in the firebox are referred to as radiant tubes. A boiler is similar to a furnace, however, it is designed to boil water for steam generation. This process changes the internal arrangement of the boiler. Water can absorb a tremendous amount of heat. When it changes state, it expands to many times its original volume. A typical water tube boiler has a large upper, steam-generating drum, a lower mud drum, and a series of tubes designed to provide natural circulation of the steam back to the generating drum. This picture shows the symbols used for steam generators and furnaces. Distillation columns come in two basic designs, plate and packed. Flow arrangements vary from process to process. The symbols allow the technician to identify primary and secondary flow paths. The two standard symbols for distillation columns can be found in this picture. Distillation is a process designed to separate the various components in a mixture by boiling point. A distillation column is the central component of a much larger system. This system typically includes all of the equipment symbols found in this video. Plate distillation columns include sieve trays, valve trays, and bubble cap trays. Packed columns are filled with packing material, rings, saddles, solzer, interlocks, teller rosette, or panapack. Reactors are stationary vessels and can be classified as batch, semi-batch, or continuous. Some reactors use mixers to blend the individual components. A reactor's design is dependent upon the type of service it will be used in. Some of these processes include alkylation, cat cracking, hydrodesulfurization, hydrocracking, fluid coking, reforming, polyethylene, mixed xylenes, and many other processes. A reactor is designed to allow chemicals to mix together under specific conditions to make chemical bonds, break chemical bonds, or make and break chemical bonds to form new products. The process it is used for will determine the shape and design of a reactor. This picture shows several examples of reactor symbols. Process and instrument drawings. A P&ID is a complex representation of the various units found in a plant shown in this picture. It is used by people in a variety of crafts. The primary users of the document after plant startup are process technicians and instrument and electrical, mechanical, safety, and engineering personnel. In order to read a P&ID, the technician needs an understanding of the equipment, instrumentation, and technology. The next step in using a P&ID is to memorize your plant's process symbol list. This information can be found on the process legend. Process and instrument drawings have a variety of elements, including flow diagrams, equipment locations, elevation plans, electrical layouts, loop diagrams, title blocks and legends, and foundation drawings. The entire P&ID provides a three-dimensional look at the various operating units in a plant. Process legend. The process legend shown in this picture provides the information needed to interpret and read the P&ID. Process legends are found at the front of the P&ID. The legend includes information about piping, instrument and equipment symbols, abbreviations, unit name, drawing number, revision number, approvals, and company prefixes. Because symbol and diagram standardization is not complete, many companies use their own symbols in unit drawings. Unique and unusual equipment will also require a modified symbols file. Foundation drawing. The construction crew pouring the footers, beams, and foundation uses foundation drawings shown in this picture. Concrete and steel specifications are designed to support equipment, integrate underground piping, and provide support for exterior and interior walls. Process technicians do not typically use foundation drawings, but these drawings are useful when questions arise about piping that disappears under the ground and when new equipment is being added. Elevation drawing. Elevation drawings in this picture show the location of process equipment in relation to existing structures and ground level. In a multi-story structure, the elevation drawing provides the technician with information about equipment location. This information is important for making rounds, checking equipment, developing checklists, catching samples, and performing startups and shutdowns. Electrical drawing. Electrical drawings in this picture include symbols and diagrams that depict an electrical system. Electrical drawings show unit electricians where power transmission lines run in places where power is stepped down or up for operational purposes. A process technician typically traces power to the unit from a motor control center, MCC. The primary components of an electrical system are the MCC, motors, transformers, breakers, fuses, switchgears, starters, and switches. Specific safety rules are attached to the operation of electrical systems. The primary safety system is the isolation of the hazardous energy lockout, tagout permit. Process technicians are required to have training in this area. This picture shows the basic symbols and flow path associated with an electrical drawing. Electrical lines are typically run in cable trays to switches, motors, ammeters, substations, and control rooms. A transformer is a device used by industry to convert high voltage to low voltage. The electric department always handles problems with transformers. Electric breakers are designed to interrupt current flow if design conditions are exceeded. Breakers are not switches and should not be turned on or off. If a tripping problem occurs, the technician should call for an electrician. Fuses are devices designed to protect equipment from excess current. A thin strip of metal will melt if design specifications are exceeded. During operational rounds, technicians check the ammeters inside the MCC for current flow to their electrical systems. Voltmeters, electrical devices used to monitor voltage in an electrical system, are also checked during routine rounds. Equipment location drawing. Equipment location drawings, plot plans, show the exact location of equipment in relation to the plant's physical boundaries shown in this picture. One of the most difficult concepts to explain to a new process technician is the scope and size of modern chemical processing. Most chemical plants and refineries closely resemble small cities. They have well-defined blocks and areas connected by a highway of piping and equipment. Equipment location drawings provide information about the neighborhood. Loop diagrams. A loop diagram traces all instrument connections between the field instrument and the control room panel. This includes instrument airlines, wiring connections at field junction boxes, and control room panels and front connections. Electrical one-line diagrams. Like the piping in process systems, the wiring in a unit follows a path. Electrical diagrams show a flow path for distributing power throughout the unit and to all electrical equipment. These diagrams show the different voltage levels in the unit, electrical equipment such as transformers, circuit breakers, fuses, and motors and horsepower required. It also includes start/stop switches, emergency circuits, and motor control centers. Process technicians can use these diagrams to trace a system from the power source to the load. Sources of information for process technicians. Information used by process technicians comes from a variety of sources. Some of these sources are operating training manuals, process descriptions, process control manuals, equipment summaries, safety, health, and environment regulations, operating procedures, start up and shut down procedures, emergency procedures, process diagrams, technical data books, detailed equipment vendor information, process variables. The process variables that a technician is responsible for controlling include temperature, flow, level, pressure, and analytical variables. It stands to reason that a study of the scientific principles associated with these variables is required for any new trainee. This study would also include the instrumentation specific to the process and the equipment associated with it inside the system. Technicians can spend a lifetime studying the unique features associated with the many processes found in the chemical processing industry. Pressure control loop. A pressure control loop design uses the 5 elements of the control loop. The area to be controlled is a special vapor disengaging cavity that allows vapors or gases that are compressible to be controlled at a set point. The one area that changes consistently is the first primary elements and sensors. Pressure-controlled loops use devices to detect pressure changes. These primary elements are typically expansion-type devices. Primary pressure elements include C-Borden tubes, helical, spiral, bellows, pressure capsule, or diaphragm. This picture includes a pressure element, pressure transmitter, controller, transducer, and control valve. An electric signal, 4 to 20 milliamperes, connects the P, PT, and PIC to the transducer where the signal is changed to a 3 to 15 pSig air signal that corresponds to changes required by the controller's set point. Pressure changes can affect temperature, level, and flow. Pressure changes the boiling point of chemicals, reaction rates, and the speed at which fluids flow through piping. These changes can impact product quality, so a variety of instruments have been invented and designed to monitor and control pressure. The instruments discussed in this video include the following: pressure gauges expressed in PSIA and PSIG, vacuum gauge expressed in inches of mercury, manometers. Pressure elements sense changes in pressure and convert to mechanical motion. Their types include bellows Borden tube, C-type Borden tube, diaphragm capsule pressure elements, helical Borden tube, pressure transmitter, and spiral Borden tube. Temperature control loop. Temperature control loop can control the amount of heat or cooling a substance is receiving, for example, steam to a kettle reboiler, hot oil to a heat exchanger, preheater, or cooling water to a condenser, heat exchanger. It can also control the amount of natural gas flowing to a burner. The burner provides heat to the boiler or furnace. 100 other applications could be described for controlling the temperature of a substance. However, the most common is by controlling the flow. This picture is a simple layout of a temperature control loop. Notice the location of the primary element and the transmitter and how the electric signal is sent to the controller. The controller compares the signal to an incoming electric or pneumatic set point. If a change is required, it is sent to the final control element. The primary sensors used to detect temperature are RTDs, thermocouples, and thermistors, often called temperature elements. Temperature elements are linked to transmitters. A 4 to 20 mA signal is sent to a controller that compares it to a set point. Controllers may be located in the field near the equipment or in a control room. The controller sends an electric signal to a transducer that is located on or near the final control element or valve. This will eliminate a process lag or delay. The transducer converts the signal to a 3 to 15 pSig pneumatic signal. The pneumatically actuated control valve opens and closes depending upon the signal. Temperature is controlled by reducing or increasing the opening on the valve. Level control loop. The following example of a level control loop can easily be applied to level control on any vessel or tank. Level control uses floats and float gauges, displacers, tapes and tape gauges, differential pressure transmitters, bubblers, load cells, capacitance probes, electromagnetic measuring devices, and nuclear measuring instruments. This picture illustrates what a standard control loop looks like. Flow control loop. Flow control loops are typically designed so that a measurement of the flow rate is taken first and then the flow is interrupted or controlled downstream. Flow control loops start at the primary element and work their way back to the final control element. Flow control primary elements could include orifice plates, flow nozzles, pitot tubes, Anybar pitos, mag meters, turbine meters, mass flow meters, nutating discs, oval gears, venturi tubes, vortex meters, target flow meters, and integral orifice flow meters. The most common primary element is the orifice plate. Orifice plates artificially create a high pressure/low pressure situation that can be measured by the transmitter. Primary elements are typically used in conjunction with a transmitter. This picture shows an example of a flow control loop. Although it appears that the primary element is interrupting the flow, this is not the case. Increased velocity across the orifice plate compensates for the restriction. The transmitted signal is sent to a controller that compares the incoming signal with the desired set point. If a change is required, the controller will send a signal to a final control element. Cascaded control loop. A cascaded control loop utilizes a series of unique features in modern process control. In a cascaded control loop, two different control variables work together to control a critical variable. For example, in some cases temperature control is more important than flow. In this case, a cascaded control loop can be used. A cascaded control loop has one primary or master controller and one secondary or slave controller. The master controller is wired to the secondary controller and has the ability to override the initial or original set point. During operation, the secondary controller operates with all 5 elements of the control system. The master controller has a 1. Primary element, 2. Transmitter, and 3. Master controller electrically connected to the other control loop. This picture shows how a typical cascaded control loop looks. Analytical control loop. An analytical control loop is typically designed to use flow to control some compositional variable. For example, the pH of a cooling water basin may be controlled by adding acid or caustic. When the ppm in the water basin exceeds operational guidelines, the analytical control loops removes a specified percentage of the basin water and replaces it with fresh water. Analytical control loops can be applied to a wide assortment of operational processes. This picture shows an example of a series of compositional control loops. Process flow diagrams, PFDs, and process and instrument drawings, P&IDs, are used to outline or explain the complex flows, equipment, instrumentation, electronics, elevations, and foundations that exist in a process unit. A PFD is a simple flow diagram that describes the primary flow path through a unit. A P&ID is a complex representation of the various units found in a plant. Standardized symbols and diagrams have been developed for most pieces of industrial equipment, process flows, and instrumentation. That's all, gentlemen. I hope this training course have refreshed your knowledge regarding to compressors and compression system. Good day and good luck.